All right, welcome folks to my talk, Engineering a Ray Tracer on the Next Weekend with the D programming language. My name's Mike, and I'm going to be talking a little bit about, again, engineering with the D programming language. Now, this talk just happens to be about ray tracers because I do a lot of graphics work. From some of you who saw my London talk in DConf 2022, this is going to be a continuation, so I hope it'll be a treat. And as noted below here, this is sort of for a beginner or introductory audience to the D programming language, but I hope most folks will enjoy it. And like the last D conference, maybe you'll enjoy just playing around with the code for the ray tracers. But with that said, let's go ahead and dive in and see what this is all about here. So again, as I mentioned, if you want to watch the previous talk, you can go ahead and learn a little bit about a ray tracer, but I'll go ahead and give you a little bit of an introduction otherwise to what ray tracing is all about and what we achieved last time. Essentially, we were able to generate this nice image here, and I talked about how I use the D programming language and some of the features of D to generate that. And I'm going to be continuing that theme with this talk today, and in order to do that, let's go ahead and just see what this is all about and who I am. Well, I'm that guy above. Should look pretty similar. And I primarily do teaching and computer graphics in these types of areas. So you can read more about me if you'd like, but otherwise let's go ahead and get into the main talk here. So this is the abstract for the actual talk if you want to read it. And again, as I mentioned, it's a continuation of the D conference talk. Now, that said, the previous talk that I gave before was just about building a ray tracer and sort of what a ray tracer is, but really it's just about showing different programming features of the D programming language. So that's what we're going to continue with. And I do want to give some attribution to the D community members who contributed some code to the previous talk. I pretty much just challenged folks to improve upon the code based off the render time, which I talked about, and the D community really rose to the occasion here. So what I must say is, if those community members do want direct attribution, feel free to reach out and I'll add you in the slide somewhere. Otherwise, you can see your names proudly displayed in the GitHub from last time. And again, for this sample, we'll also have the GitHub, and I'm happy to open that up if you want to fork the repository or do any pull requests to improve upon the code to help others in the D community learn. So with that said, let's go ahead and continue onwards here. So again, I want to pick up from where we left off, and the standard sort of image that we generated looks something like this from our previous talk here on the D programming language for building this ray tracer. So what does that mean here? Well, again, if you want, you can follow along from the code repository here in the GitHub, or as I said, perhaps make a contribution if you'd like. But with that said, here's just a brief recap on ray tracers in 1 minute in case this is your first time attending DConf online and aren't sure what this is and haven't had a chance to look at those other talks. But basically what we've done is generated some image like this. It looks quite beautiful in a way. We've got reflections, we've got shadows, and typically when we build a ray tracer, we do spheres because they're an easy shape mathematically to represent. So we have something like this. I'll get out of the way for a moment so you can see the entire scene here unobstructed. And here's the general idea of ray tracing. Basically this idea where you could imagine yourself in the middle of the screen here with a laser pointer, shooting that laser pointer through each pixel in your screen. And then every time it hits an object, you essentially say, hey, what color is that object? And the first object that you hit is the color of the pixel of the screen. That's the general idea for ray tracing. Now, of course, there's a few different strategies with ray tracing, so feel free to take a graphics course or read the great Ray Tracing in 1 Weekend books by Peter Shirley, which have been linked in the previous talk, or you can go ahead and just search that. But again, depending on if you're casting rays from someone's eyes or the lights will differentiate the types of scenes that you can actually generate. So that's ray casting, and that's the general idea. Now, as you can imagine, we are casting lots of rays because we have lots of pixels on our screen here. So that means we need performance. And in a way, that's what we're going to be talking about today, engineering and the performance of this ray tracer. So from the previous talk, I left you this slide here on how long it took me to generate this background scene. And that was one of the challenges here, that it really took a lot of time here. So some different renderings, depending on the different scenes that I was making, we're taking about 14 or 20 minutes. And as you can imagine, that's a good deal amount of time. But again, the D community rescued me and showed me some ways to improve the inefficiencies in some of my code. And in the process, well, I learned quite a bit and want to share that with the community and just talk about why D is a great language for doing performance and systems work. So let's go ahead and show off some of those features here as we dive in. Now, a great place to start here when thinking about how to improve the performance is to actually do some profiling and figure out where are we spending time when generating some scene like this. So this is the type of scene that we're going to be working with, just a standard two spheres here that can reflect, and then another sphere here, and you can see some shadows. So enough interesting stuff that's going on that we could collect a good profile from. Now, built into the D programming language is a profiler, which is really, really cool. I'll talk a little bit about other profilers that exist towards the end of this section, but just having this built in and available in the D compiler, I think is something of great value. And there's really two types of profiling that we have here. So highlighted here, and you can follow the link below, we have CPU profiling, where we can essentially just instrument every function at the start and then all of the return blocks in that function and figure out, well, how much time did we spend in this function? How many times did we call that function? It gives us a rudimentary metric of how fast or slow our program is, or where we're spending a lot of time and where we might want to optimize. And then likewise, we have another profiler for heap profiling. Memory allocations are actually quite an expensive part of the rendering, or really any application that you run. Heap memory and heap allocations take quite a bit of time to find memory, free memory, and so on. So having a built-in profiler to tell us where we're allocating can directly, again, tell us where we can improve on performance. All right, so how do we enable profiling using D? And in particular, I'm using the DMD compiler for this talk. Well, it's actually as simple as just enabling this switch here for profile, which I've highlighted above here on my command line where I'm compiling all of my code. Now you'll notice I'm also going to be compiling with debug symbols here. That we'll get rid of when we want to do a true profile and get the true number or the true time of how long it takes to build our scene, but we'll revisit that in a moment here. But what does dash profile give us when we actually run our program? Well, what'll happen after we run and execute our program here, so the next part of this command line here, is we'll get a trace.log file and as well a definitions file that lists all the different functions. And we can see towards the end of that file, so you can see towards the bottom of the file here, the number of calls to a function, how much time we were spent within this function sort of call tree, the actual time spent, and so on. So these are the different types of metrics that we have here, and they're actually sorted here, so we can kind of see, hey, this first one's interesting. We're spending a lot of time there. So that gives us, after running this profile, a sort of baseline here, so we can see where we're actually spending our time. And just to go ahead and start this experiment, we want to figure out, well, how much time was our actual program running here? And I'm going to go ahead and just use on a Linux system the time command here, which will give me various measurements of how much time we're spending, the real time, time in the process, or the system time while performing this rendering of this scene here. So it'll give us a sort of good benchmark. And right away we can see, well, to render this on my particular machine here, it's about 1 minute and 12 seconds. So that's what we're going to want to improve on. So let's see what silly mistakes I was making and how we can improve on them using D properly here. Okay, so the first thing that we want to do, again, to make use of our profile and this information is, again, to start with the most popular function. So usually that can mean the function that's called the most or the function that we spend the most time in. And that's sort of what's known as a hot function. So again, in our profile, we'll go ahead, look top to bottom here, and notice that this generate random double function is of interest. It's in the utility module, and it's something that returns a double here. Okay, okay, so this is interesting. A few folks actually caught this from the last talk. while I was showing it, and they knew it was probably a gotcha. So here's the actual slowness of the code here. And you can go ahead and just kind of look up at this code here and see I am doing something silly. I didn't realize it at the time here, but this is a common thing that might happen and why it's important for you to really be a disciplined engineer and profile your code. So here we can see that I'm essentially setting up a random number generator here over and over and over again. And how a lot of these random generators work is they'll generate a bunch of random values, which takes some time for that function to actually execute. They might actually be doing maybe allocations behind the scene to store that non-deterministic or maybe deterministic, depending on the random number generator, that sequence of numbers. So we can imagine this is something expensive. That's what our profiler told us, at least, that we were spending a lot of time here. So repeatedly doing this operation every time I'm calling generate random double, and if I go back to our profile here, then you'll see that we call this 4 million times, almost 5 million times. That's going to be quite expensive. So again, let's go ahead and see how we can fix this. So there was a little trick I learned from some members in the D community, Ali Shirelli's book, and some other from some experience from other programming languages. But the trick is, well, if we only need that one sequence of random numbers, let's just initialize that one time. And D has a nice capability here where we can run for this module, whatever our module is in, and again, I'm borrowing from Ali's book here, to initialize our random number generator here. So in a way, you can kind of think of it as our global variables. Or in other languages, it's sort of like having a singleton class or a startup and a shutdown function where you can just sort of set things up all at once. And there are some different things you might want to consider if you have multiple threads, so looking into shared static this, but this is going to do the trick for us now. So let's go ahead and see how we apply it here. And what I've got here is just using this trick here, global for our random number generator. And for this module, we're just going to go ahead and set up our random numbers just one time here. And then just like that, the actual application in our function here at line 17, 18, and 19, we'll just see that we can just generate the next number using a uniform distribution here. So something that's sort of like a bell curve. And we don't have to constantly create this random number generator. So that's great. Let's see if it actually made a difference though in our performance. So again, I'm going to measure using the same flags as before. So pretty much the same as everything, just that one change with the random number generators. And immediately we can see a great impact here where we're going down from 1 minute and 12 seconds down to 15 seconds. So this is, quite amazing here. So let's go ahead and see what we can profile next and see if we can keep improving our program here. And again, this is a very iterative way to develop, but it's part of the process here. And again, we're going to uncover some nice features of the language here that we should understand with programming in D. Okay, so the next profiled run, again, repeating the same exact process, it looks like vec3 is the next interesting function. And in particular, it looks like it's calling this overload here for the minus symbol here. So maybe we're doing lots of operations where we're differentiating between two vec3s or maybe 2 points representing vec3s to give us a direction. Something like that in the domain of ray tracing is what we're doing. But anyways, we can again see that we're calling this function many, many times. So again, let's go ahead and see if we can make some improvements. Now, this time I'm sort of noticing something that's interesting here, and we're going to venture into that other profiler that the D programming language has. So if I go ahead and compile this time with profile and then equals GC, we're going to get a profile that actually tells us about the heap allocations that took place. So remember last time I told you heap allocations take a lot of time. We have to ask the operating system to find us a page of memory, usually handed out in a page, and sort of allocate that and divide up the chunks of that page to, well, however much memory we need for a vector 3 in this case. So that could actually be quite expensive. So let's go ahead and take a look here. Well, here's the performance problem, as I mentioned, where we're doing lots of these binary operations here with vec3, and in particular, it looks like we are doing subtraction a lot here in this overload that I have here. And that's the big offender that we have here. So let's go ahead and just see if we can get rid of this new to avoid a heap allocation and just allocate on the stack. So I'll go ahead and get rid of that there. No problem. New has been erased. Uh-oh. Looks like I'm getting a list of compiler errors. Okay, so what happened here? I'm getting all these, well, what look like scary things here. No property opcall. And this is being repeatedly said and saying, hey, did you mean new vec3? Well, no, I didn't. I actually wanted to get rid of that. But let's see what the silly mistake is that I might have made here. And the reality is I modeled vec3 as a class here. So we've got to be a little bit careful. So if you're coming from a different background, like a C++ background, which maybe for many of you, it's certainly the case with me, there's no real distinguishment between class and struct. But a lot of modern programming languages, and D being one of them, has actually sort of made a difference known to a struct and a class. And the difference being that structs are, well, value types. So when we say it's a vec3, we really mean that it's just a vec3. There's no inheritance going on or polymorphism. There's no hierarchy. So that's the difference with a struct. Of course, we could still allocate structs on the heap if we wanted, but really we just want to treat this as a vec3, something that's holding 3 floating point values. So that's sort of the difference and something that we need to think about. And from a design perspective, just knowing that there's not going to be any sort of type checking that we have to do, or checking, what a particular piece of data is a win-win from a sort of design or a abstraction standpoint. Now, with a class, that's where you do have to allocate something on the heap here. Again, because it's a reference type, you have to determine if it's, well, just a plain old object, which everything's inherited from, or something else down the hierarchy using single inheritance. So let's go ahead and change this to a struct here, and I'll move out of the way so you can see things. And it looks like that's going to do the trick here. Now, I did have a default constructor here that I had to remove and refactor as well, because that's not allowed in the language here. So I just created another constructor here for one value that'll set up the other 3 values. And it looks like, that's going to do the trick for us. Now, there are going to be some places in our code where I'll have to remove new vec3 where that's being used, but let's go ahead and see what the difference is with our allocations. And after the fact is, I can go ahead and run profile with equal gc to see if there's any allocations being made. And I can tell you by just looking at the top in our list to find the most allocated object, well, I can actually tell you in the entire file, it never showed up. No allocations for vec3. They're all on the stack. And that's a great thing that we have this control, because the stack is often something that we'll say is very hot and that it can be very performant. Just push and pop information on the stack and then it pops off out of scope. So no allocations for vec3, and let's go ahead and see how much that improves our speed. And just like that, with that making a struct, so being very specific and improving our design, and then also getting rid of the allocations, we're cutting our speed in half again. So we can already see that our user time spent in this process, is roughly half here at this point. And importantly, we'll see that the system time is also decreased here. So if we have other processes running, then those processes get access to the resources that they might need. And again, we're not fetching memory and having to search for memory, and that's where you can really see it on the system time here. All right, so one more round of removing some allocations because, well, admittedly, as this project grew larger, I had a few other things I didn't think about. So was it going to be a class or a struct? So something that we have to think about in the D programming language. And that's a good thing because we're thinking about our design. So after one more round of this and removing anything that shouldn't have been a class and refactoring it into a struct and removing heap allocations, we're down to just under 6 seconds here for our process. And as I mentioned, eventually I'll get rid of this -G flag, and we'll even see that when we're not doing debug builds, we can get even more performance here. So now we're at a really reasonable iteration speed for designing some scenes with our ray tracer. So let's go ahead and continue on. So the question is now at this point, and I have to think about this, is where am I going to get more performance? I've kind of done the baseline. I've structured our ray tracer. I've removed some heap allocations. At least the two that come to mind are, well, what can I compute in parallel? Because that's a way that we can get things done faster if I can do multiple things at once. And then secondly, the other way to speed up our program is to remove work. Just remove computation, and that should also make the program faster. So let's go ahead and start here with just seeing what we can compute in parallel. So this is going to be our first strategy to further improve the performance of this ray tracer here. Just do things in parallel. Again, we have multiple CPUs, we pay good money for them, so if we can have them work on independent tasks, let's go ahead and do that. And it turns out a ray tracer is a very parallel task. And that means that if we're casting little rays out for each of the pixels, those can happen independently. Now the deprogramming language, if there is some dependence on order in the standard library, has a concurrency library and other asynchronous mechanisms that we can use, but well, we've got std.parallelism here that we can use here. So this essentially allows us to very trivially, in some cases, enable parallelism in our code. So let's go ahead and see an example of how we can use this library in the deprogramming language. So the thing that we want to look for is, where do I have a bunch of independent tasks? Now I'm giving you a little bit of a cheat sheet here because I know where to look exactly in the code, but anywhere where we're casting those rays in our program for each pixel on our screen, that's a pretty good candidate. So here's our code, and you can see at line 74 and 75 what I've refactored at the commented out line 76 and 77, where we're doing things very sequentially, looking at every single pixel in our screen here. Well, why not just go ahead and say for each of those individual pixels here, and iota gives us a range, and Ali gives us a really nice talk here if you want to go ahead and learn a little bit about iota and ranges in the deprogramming language. But we can simply just call .parallel on it, and that's going to go ahead and fire off a task and essentially give us parallelism for free from a development perspective. We don't really have to implement a complicated threading system or go into GPU code. We can just try this out. At the very least, the nice thing is that we can just have this mechanism to try out and see if it's going to make things faster. So that's important, to have some of these constructs and see if it's worth, further hand tuning if we needed to. Let's just go ahead and see if we get a boost from this parallelism here. So the result is, for our project is, well, just with this little tiny refactoring here, we're now running at about less than a second here. So 769 seconds here, 0.769, or 769 milliseconds. And you'll notice that the user time here is still around 11 seconds or so, so that's actually gone up. But now we really care about the real time. That's how much time, if you look at a clock, sometimes known as clock time, or the wall clock, is actually taking place. But since we have multiple CPUs all processing independently, casting rays out into our scene to compute this image, that's what the user time is accumulating. So you still want to keep an eye on that, but now the real time is going to be a more meaningful metric for us. So this is a great progress that we're making here. So let's go ahead and continue here to our second strategy and see how else we can improve performance. And that's by using D to reduce computation. So now one area where we're doing a lot of computation that maybe we want to reduce here is the opBinary. Again, this was something that was pointed out to me in my original code by community members, saying, well, if I've already got this templated sort of function here where I'm doing the overload here, what if I could sort of fold these operations and avoid the comparisons that we're doing here? So let's go ahead and see what that looks like in our code. And D's got a really great feature for doing something known as a mix-in here. And basically what this means is at compile time, we're going to go ahead and just generate the code that we need for this operation here. So if I'm using plus in my program, we'll go ahead and get pluses here for how to add two vectors together. And likewise for multiplication, division, subtraction, or maybe any other operators that we decide to add later if they have any meaning. So that's pretty cool that we get this. It's going to make our program both a little bit more future-proof and more efficient. Look, there's no branching here, no if or else statements. So if we go ahead and run this, again, now looking at our real time here and our user time both have meaningfully dropped here. And that's after a series of tests here. We like seeing this going down here. That's great news. All right, let's go ahead and continue here and actually do some real benchmarking here now and see how much the compiler is going to actually give us with the release build. So we're going to do things like remove the debugging symbols, which we don't need the debugging symbols when we're going to deploy this to some actual client. And we'll also be able to use these capabilities for optimizations. So when we go ahead and set up a release build here, what we're going to do here is just use the compiler flags that are recommended here, turn on optimization, set it up for release, maybe turn on some specific optimizations like inlining, and turn off bounds checking once we're pretty confident that this program is going to be working. And with this benchmark here, pretty incredible results here. We're down to 0.282 seconds. And again, algorithmically, there's probably more that can be done here. We can probably have things like bounding volumes and other spatial partitioning data structures for those who have done a little bit of graphics work, and probably improve this time even more for thinking about casting our arrays. So that's pretty incredible, though, that we've gone down from what was about 14 or 15 minutes a few months ago when I was first working on this to 0.282 seconds. So again, as I mentioned, profiling itself and running experiments is a pretty deep topic. I'm going to go ahead and sort of end our journey on profiling here as we're nearing the end of the talk here. But there's a nice talk here from DConf 2021 by Max here. So you can go ahead and check that out. And at the very least, it's good to know that there are tools built into D that everyone can use by default. Other profilers like perf are very nice and can give you more information like cache hits and misses, so you might want to go dive into that later after doing your preliminary investigation with D. All right, now we are doing some engineering here and our project's growing. So how are we going to set up our project for distribution or if we start adding other dependencies? Because you could imagine this growing into a real project. Well, the great thing about D is we have an official package manager here, dub. And I think that's become a real important thing on real engineering projects. So this is the tool that we can manage our dependencies on. I like showing everything on the command line because that's just a way to learn. But once you know a little bit what's going on behind the scenes, using something like dub's pretty easy to use. You can just run dub init in your actual project here. And here's the actual physical file structure of our code here. So you can see I've moved things into source here. I've got my output directory, and here's my ray tracer that's going to run here. And all the dependencies and specific versions of your software can be found in the dub.json file. All right, so let's go ahead and modify our ray tracer and just do a little bit more engineering on it. Again, we want to make this sort of an interesting tool and something that you can actually play around with. So the great thing again with D is it's a programming language and an ecosystem with batteries included. The standard library here is quite loaded with interesting things that you might want to do on a daily task, like working with zlib for compression, JSON, curl, socket libraries, CSV, etc. Many of those common things are available, so be sure to check out the standard library documentation here. But what I want to go ahead and do is just proceed a little bit and use JSON to set up our scenes here. That'll make things a little bit easier to iterate on. So here's a piece of code here, just playing around with a JSON. And again, no external dependencies. It's just here in the D programming language for me to use. I just import standard.json, and then I'm able to parse files that I've read in as text here. So you can see me reading in the text here at line 66. and parsing it at line 70. And then I'm just going to populate and create my spheres based off of some of the properties here. Now, this might be something that I want to iterate on later and maybe use some nice patterns like a builder pattern to actually build up these objects, but here's just a quick and dirty thing to end the talk with. And here's the actual scene that we've been rendering with our actual objects, but now they're in JSON. So our application in a sense has become data driven. We're just parsing this file now and creating the objects based off that input. And as we near the conclusion here, let's go ahead and see what we're able to do. So if you've enjoyed this talk, if you've found some value and want to see some of the refactorings and kind of get into the deprogramming language, as I've been writing this talk and refactoring it along the different ways, I've documented with some commit messages and the changes to each of the files here what was done. So please feel free to grab the code off of GitHub if you want to take a look here. My hope is this will be a great project for new folks in the deprogramming language to learn from. The deprogramming language playlist is still alive and well. That was something I announced at the DConference in 2022 at London. And feel free, if you have ideas, to ping me on Discord. I'm sometimes active there. Or, of course, email me if you have other suggestions or things you'd like to see there. I do have some exciting news that I'm actually going to be teaching in the deprogramming language. So, as always, I like to leave you with something fun here towards the end. So let's just go ahead and show one more image here as we wrap up this talk here. And again, I was just taking advantage of that JSON file to have a little bit of fun here. And for our last image, we've got to have, again, a D here and just some other spheres here reflecting that image here. And in theme with the talk, learning a little bit about some engineering. Well, this time we're down to just 39 seconds to render a full HD image, so not too bad. And I'm sure by leaving you this scene file, you'll have something a little bit more interesting to start thinking about how to optimize. So I'll look forward to folks at the next DConference to continue improving upon this code and seeing what you can do. I think there's a lot more room with different compilers to keep improving on this. And with that said, folks, thank you so much for your time. I'm happy to take questions now or in the future in the comments. And I then want to just go ahead and take a moment to thank the D community for inviting me to give this talk. I hope you learned something interesting. Again, if you were a beginner and got to see some of these different refactorings that can make a big difference in the quality of your code for performance and even the organization. So with that said, thank you again, D community, for your time. I'll look forward to seeing you at the next one.